I got just a review exercise for you here to start. Can you read that in the back? Is it big enough? Yeah, there's some thumbs up. Okay, so this is review. So I'm showing you a contour plots. This is an XY plane, but it's showing a multivariable. It's representing a multivariable function. X and Y are independent variables, and these are constant Z values. So that's a representation of a multivariable real valued function. And I got this point 2, 2, and I've got 4 questions for you here. So I want you to work on these. You can think and make progress by yourself, or I always encourage you to discuss amongst yourselves. Okay? So your answers will be then expressions. Okay? So it's not all going to be like numerical answers, but you might have to write down expressions that represent the answer to the question I'm asking. So you're making progress, or you're getting help. Okay, here we go. So rate of change of f in the x direction at 2, 2. An expression that gives that exactly. What do we think? Yeah, Andrew. He wants this. Agree? Yeah, I'm exactly asking for the partial. What that phrase is asking for the partial derivative with respect to x. What's the rate of change in the x direction? That's the partial derivative with respect to x. So f of x 2, 2. Right? Okay. How much does z change if x changes by negative 0.04 from 2, 2? So how much? So if now I'm gonna make a little change, negative 0.04. Meaning I'm going to go in the negative x direction. And what expression would then calculate the corresponding change in z? Jackson, did you get it?
I was thinking it would be dz equals negative 0.04 dx.
dz equals negative
M.
Yes. Okay, so what is m? So what is the rate of change that we need if we make a change in the x direction? Yeah, so exactly. dz equals m dx. Perfect. So now what's the rate of change and what's dx? What's the rate of change in the x direction? That, not of x, right? The partial of x with respect, or the partial of f with respect to x. And what's dx? Negative 0.04. So that's it right there. That will give the change in z. The rate times the change in x gives the change in z. And since we're going in the x direction, the rate we can use is the partial with respect to x. Does it make sense? Did you get, what about, how much does z change if y changes by 0.01 from 2, 2?
It's like the same thing, but
Yep.
the partial with respect to y.
Okay.
Times the change in y, which is 0.01.
That's dz. dz equals m dy as well, if you have the right m, right? So now the rate in the y direction is our partial with respect to y. All right, so now both changes are going to occur. We want to do both changes. How much will z change? So what is my dz? I want to write expression that gives me the dz if both of those changes occur. Ryan, did you get it? Exactly. So it's going to be m dx plus what? M dy. But you got to have the right m's, right? So you got to have the right rate. So you're going to have the change in z that resulted in the change of negative 0.04 in x. And for that, you use the partial with respect to x, that rate of change. And you're going to have the change in z that resulted from the change in y. To get that, you need the rate of change, the partial with respect to y, that rate of change. Okay, so now we're gonna consider those both happening together. And so what kind of change, what would that be like? Making both those changes together. So here's our point at 2, 2. What would that be like? The change of x of negative 0.04 and a change of y of 0.01 occurring simultaneously. Where would I be going from here? To the left and up. And in which direction am I going more? Yeah, so left a lot and up a little, right? The left, in fact, up, like to the left 4 times as much as going up, right? So something like this. And that's not, it should be even more shallow than that. But basically, with the ratio of negative 4 to 1. So there's this, so we have the rates of change in the x and y direction, and now we're talking about rates of change in other directions, which result from combinations of changes in proportion, right? So now the proportion of change that I'm talking about is y is going to increase 1/4 as much as x decreases. And that's a particular proportion of x and y, and that gives us a direction from 2, 2, particular direction from 2, 2. So we can express that direction 2 different ways. We can express it as a vector. So what vector would express that direction that I'm talking about? What vector would express that direction I'm talking about? Okay, negative 4, 1, and as a unit vector. So let's say I just want direction and I don't care about the magnitude of it. So the unit vector would be negative 4 over root 17 and 1 over root 17. So that unit vector expresses this particular direction where changes in y and x are in this proportion. The change in x is negative 4 times as much as the change in y. Another way to express that direction is and the standard trig angle, right? So there's a theta. There's a theta from the standard trig angle that gives that direction too. So both those, and what this theta is like something like what? Tangent inverse of something, so whatever that angle is, right? Or like cosine inverse of negative 4 over radical 17 would give that angle. So what if I want the rate of change in that direction, right? So I want the rate of change in that direction. So the rate of change would be what? It'd be the same as dz, the same dz as if I moved 1 unit in that direction, right? So if I move 1 unit in that direction, the dz that I would get would be the same as the rate of change in that direction. Does that make sense? So what is that? We can change this to then f of x of 2, 2. What? Negative 4 over radical 17 plus so doesn't this force me to go 1 in that direction of negative 4 to 1 proportion? Because instead of using the negative 0.04 and 0.01, I use the x and y components of the unit vector. So now dz and the rate of change are the same for that. This is if I go length of 1, then now this is the rate of change. And I can write this So if I want to see, this is the unit vector. If I make a vector out of these partial derivatives, then what vector operation am I really doing here? This is really the dot product. So I'm taking a vector of the partial derivatives dotted with a unit vector in the direction I want to go, and what do I get? I get the rate of change in that direction of z, rate of change of z with respect to going in that direction. Okay, so this, the vector of the partial derivatives is called the gradient, and you express it this way. Okay, if your function is called g, then it's gradient g. It's f because the name of the function here is f. And then this is the unit vector in the direction we're interested in. So that's u. And then going up here now. The notation for the rate of change in any direction u is capital D sub u f x y. And this is called the directional derivative. And what does it equal? It equals the gradient vector dot the unit vector pointing in the direction that you want the rate of change in. Okay, so u could also be expressed, right? An alternative way to express u is through theta, right? So it's any way you can express the unit vector in that direction. So we can do it as in components or using theta. And so what would be using theta? Cosine theta and sine theta, right? Cosine theta, x component of this forces it to have a magnitude of 1, and then we got x direction and y direction, right? So when you do these problems, sometimes you might do it with theta and you use cosine and sine, or other times you'll just create, you know what the vector is, you know what the direction is, you just create the unit vector however you can do it, using theta or not. So it's the idea of if you're standing on the side of a mountain, like the mountain surface is the mountain face is your surface, and you're standing on the side, and you're asking, what's the rate of change? What's the rate of change on the side of the mountain? Well, it depends which way I'm going to step, right? And how many rates of change would there be? So imagine I'm on the side of a mountain. The side is, I'm on my way up. I'm hiking up the mountain on the trail, right? So what's the rate of change where I'm standing of height with respect to horizontal? What's that? Depends on what direction, right? And how many rates of change could there be? Infinite number, right? So if I turn this way, I might take a small step up. If I turn this way, maybe this is a big step up because the top of the mountain's that way. If I turn this way, I might take a small step down. If I turn this way, maybe a medium step down, right? So I've got there's an infinite number of rates of change as depending on which way I go on the side of the mountain. So we started with the two kind of reference directions, the x direction, and the y direction. But now we have a way to get the rate of change in any direction. Does it make sense? Okay, that's called the directional derivative. And you take the gradient, you make a partial derivative, you make the vector of the partial derivatives, and dot it with a unit vector. Okay, so let's look at do an example. Okay, any questions on this so far? Okay, so here's that same thing. Now I'm showing you both the surface and the contour plot. There. That was our same point. And this is what? This is an elliptical paraboloid. Okay, elliptical paraboloid with its vertex at. I'll look at the function here. So f of xy equals 1/2 x squared. Sorry, negative. Yeah. Negative 1/2 x squared minus 1/4 y squared plus 4. Elliptical paraboloid vertex 0, 0, 4. Opens downward, right? It's elliptical because I have different radii in the x and y direction by those denominators. Okay, so if we're thinking about directional derivative, then what we're considering here so here in the xy, we're considering a circle around our point. And we're considering what direction do we want to go in, and then what rate of change will we encounter if we go a little bit in that direction, right? So now for the surface, that same circle looks like this in the xy plane. Okay, so I got my point 2, 2. Well, that point 2, 2 then has a z value, gives me that point up on the surface. And so we have to orient things, right? X is coming out at you and y is to the right over there. So if I look at the direction here, my direction here. So what is this? This is theta equals what? 0, right? In both cases, theta equals 0. Positive x-axis, whether that's coming out at you in our three-dimensional plot or to the right on our two-dimensional plot. So you have to see that I'm showing the exact same thing here, right? I'm showing the same thing. And so then if you increase theta and change that direction, here's what that looks like, right? I'm going counterclockwise from positive x. So I'm showing you the exact same thing in two different representations. Do you see that? So what I want to do is I want to find, I'm going to look at pi over 3. So I'm interested in the angle theta pi over 3. So this is showing the same angle. Both is showing the same angle. I want you to find the rate of change of this surface in the direction pi over 3 at the point 2, 2. Right? So we have a starting point, 2, 2. Direction, pi over 3. What's the rate of change of z for this surface at that point in this direction? See if you can do it. Before we start, let's predict. What can you predict about the answer? Let's predict about the answer. The rate of change. Someone said negative. Agree with that? Yeah, because if you go a little bit in that direction, what will happen to z? It will go down, right? So we expect a negative rate of change. Okay, go. Curry, did you make any progress?
Now we found the derivative of fx and fy.
Okay, that's good. We're going to need that, right? Because the rate of change, how are we going to calculate the rate of change in general?
Just take the derivative of x.
Okay.
and the z.
Yeah.
I got negative x minus 1/4 y squared.
Negative x, right? And
No, that should be fx. No.
that's the partial with respect to x. What's the partial with respect to y?
Um, I don't know.
You said you found the two derivatives, right?
Yeah.
So what was the
Exactly.
partial? Yeah, just tell me what the partial with respect to y is.
Negative.
Negative
So 1/2.
1/2 y, right? Okay, so then if you put them together in a vector, that's called the gradient. And the gradient is part of what we need to calculate the partial with respect, or the rate of change. So then we want the gradient at, so that's a gradient function, right? So this is what is this? A vector function, right? So the gradient is itself a vector function, a function of ordered pairs x and y, and we want particularly where? 2, 2, right? So what is the gradient at 2, 2? Negative 2 and negative 1? So there's a gradient as a function, you just the partial derivatives as functions. So that gives you the partial derivatives anywhere for any xy points, and then we're interested in at 2, 2. So that's negative 2, 1. Okay, take over from there. Let's see. Serenity, did you get anything else that helps us solve this? Uh-huh. Okay. So it sounds like you're talking about the unit vector. The unit vector is? So cosine pi over 3. And that is what? 1/2 radical 3 over 2? So given the direction pi over 3, this is the unit vector in that direction. Rate of change? You get the rate of change? We do? Dot product, right? So we want directional derivative. D sub u f22 is going to be that dot that. And we get negative 1. And that's definitely negative, right? So what does that number mean? What does that number mean? It's a rate of change. Yes, it's a rate of change. And what does that mean? Tell the person next to you. That's a rate of change. Tell the person next to you what it means. Okay, let's see. Jorge.
I said it was z changes -1 minus root 3 over 2 in the direction of pi over 3.
That's how much, that's dz, that's how much z changes? That value?
That's what I thought.
Okay. You shook your head, Winston. So
That's like what you would, that's the slope that you multiply dz by in that, but it is in that direction of,
so start from the beginning. This number means what?
it's the amount that, it's like the multiples that you would multiply the change in z by if you have a change in z in the direction of pi over 2.
Okay, you keep using change in z. There's another change, yeah.
At 0.22,
Yeah.
If you move 1 unit to pi over 3, z changes -1 minus root 3 over 2 times that change.
Okay, so does it have to be 1 unit in the direction of pi over 3? So?
Any direction, any amount of movement in that direction.
Right. Given any change in the direction of pi over 3, z will change by how much? This amount times as much as how much you decided to move in that direction, right? Goes back to dz equals m dx or dz equals m dy, but now the direction is not x or y anymore, it's in this direction. So maybe like call it du or something. There's really no good notation here, but given a change in the direction of u, the change in z will be this much times that change in the direction of u. How much z will change. Okay. Questions on that example? Yeah, please.
So when we have cosine and sine for u, because the unit circle it's already unitized, is that why we
Cosine and sine are, by definition, they're coordinates on the unit circle. So you'll always have magnitude 1. So cosine and sine always give magnitude 1. Because by definition, those are coordinates on the unit circle. Other questions? Yeah?
Does it have to be like the same ratio of x and y, or it does, doesn't it?
What do you mean?
Like if you're going to write out this the dot product of the unit vector. Oh, I guess it doesn't have to be the unit vector then, so it does have to be the same ratio.
Once you pick a direction, once you pick a direction, a unit vector direction, then your x and y are proportional.
Yeah.
Is that what you're saying?
Yeah.
Exactly. Yeah. But to get the directional derivative, you have to go 1 in that direction, right? Yeah. Yeah, but your change in, when you make a change along the unit vector, your x and y changes will stay in proportion. Yep. Other questions? Okay, so let's formalize and take this a step further here. Okay, so directional derivative is the derivative in the direction of theta, and we've been through this. We know it's the partial of x cosine theta plus the partial of y sine theta. And so we made it into dot product. The dot product of the gradient and the unit vector. And the gradient is like an upside down delta. Don't really know what that thing is called. Is there a name for that? But if it's bold, it's a vector, so it's either bold or you put an arrow over it. One of the two. Put an arrow over it, or it's bold, and that means vector. Okay, and this is, again, this is the directional derivative, the direction of u of xy. So this is all just review. That should be xy. Didn't get them all. Okay, so there's another way to express dot product. What was the other way besides multiplying the corresponding components and adding? There was another way to express dot product. What was it? Multiply the magnitudes times cosine of, now what angle would we be talking about? The cosine of angle between the vectors, right? Is that theta? No, right? So these two vectors have an angle between them. Theta is the angle swept, is our reference angle swept counterclockwise from 3 o'clock, or from the positive x-axis. So the angle between them, we need to call it something different, because it's not theta, what we're using for theta. So we'll say alpha, okay? So what is alpha? Alpha is the angle between these two vectors. But what is the magnitude of the unit vector? It's just 1. It's always 1, right? So that just goes away, right? So that just goes away because you're multiplying by 1. So you can say another way to calculate the directional derivative is the magnitude of the gradient times the cosine of the angle between those vectors. Okay, note, not theta. That's totally different than theta. Theta is the angle between you and the positive x-axis. This is the angle between you and wherever the direction of the gradient vector is. Okay, so when we talk about the fact that you're standing on the side of the mountain and there's all these different rates of change that you could end up encountering depending on the direction you went, well, that begs the question, which direction is going to give us the max rate of change, right? So if you're on the side of the mountain, there's some direction that would result, if you took a step, would be the biggest step up, right? That would be the direction of max rate of change. So if we want to maximize this, what do we have control over here to maximize that quantity? I mean, we're choosing direction, right? We're choosing direction. And so the alpha has to do with direction. So how are we going to make this whole thing the biggest it can be? Yeah. What's that? The biggest that cosine gets is 1. So we want cosine alpha to be 1. And so what would that mean? If cosine alpha equals 1, then the maximum rate of change is what? The magnitude of the gradient vector. Do you see that? The maximum rate of change, or the highest possible directional derivative, is going to be the same as the magnitude of the gradient vector. Okay, and then in what direction? So the maximum value of the gradient, or the directional derivative, is the magnitude of the gradient. And in which direction should we go to get that maximum directional derivative? So what alpha is going to make cosine alpha equal to 1? 0, right? So what does that say? What u are we going to pick? What direction are we going to pick so that alpha is 0? The direction of the gradient, right? So if alpha is the angle between u and the gradient, u is the one we get to choose. And we need to choose alpha to be 0. Well, that means we're going to put u in the direction of the gradient. Doesn't make sense. So the maximum rate of change, maximum directional derivative, it's all about the gradient, right? It's all about the gradient. The magnitude of the gradient gives you the max rate of change. And the direction of the gradient is the direction you should go to get that max rate of change. Okay, so for the example, the function I gave you at 2, 2, I want you to find the max rate of change and the direction you should go. For the function, the last example we did, what would be the maximum rate of change at 2, 2, and which direction should you go to achieve it? Okay, and so sorry to interrupt, but let's just, looking at the picture, let's predict that first, and then see if the numbers work out. So I can choose any u I want, right? And now I'm interested in which direction would result in max rate of change. So first of all, does that look like it's in the first, second, third, or fourth quadrants? Someone said third. Any other nominations? Or do you agree with third? I want the direction of the highest positive rate of change. So here's first, second, third, fourth quadrants. Agree with third? Something like in here, right? John?
Wouldn't there be two maps, like directions like that and the opposite of it?
Positive, maximum positive.
Oh.
Yeah, so there'd just be one, right? But yes, you're absolutely right, and we'll talk about negative in a second. So somewhere in here, right? Somewhere in the third quadrant. Go. Somewhere in the third quadrant. It's going to get me the max rate of change. What was the gradient vector at 2, 2? -2, -1. So max rate of change is? Max rate of change is square root of 5, right? The magnitude of the gradient, right? And in what direction should we go? So, right. So if you had that, then the unit vector would be the unitized version of that. So -2, -1, meaning to get max rate of change, you want the proportion of changes of x and y so that x is twice as much as y, right? X is 2 times as much as y. So what would that be like? Let's see here. Maybe it's easier to see here. So is that like this, exhibit A, or is that like this, exhibit B? Exhibit A. It's like that, where the proportion of x and y changes is 2 in the negative x direction for 1 in the negative y direction. So this is the gradient vector. That's the gradient vector, -2, -1. Its magnitude, radical 5, is the rate of change of the gold surface, z, with respect to going in that direction. Now look at the contour plot. What do you notice about that direction? So let's highlight the contour line that we're talking about here. So 2, 2 is on that particular contour line. I've made it more bold. What do you notice about that direction? Relative to that contour line. What's that?
It looks like we're talking to, right?
It looks like it's orthogonal, right? Does that make sense that it should be orthogonal to the contour line, the direction of greatest rate of change? What? I think it's cool too.
It's wild because the fastest way is a straight line.
Right, because it's like, this is like your fastest way up would be the quickest, getting to the next contour line as fast as you can would be going in what direction? Orthogonal, right? So if you want to get to this next line as quickly as possible, you're gonna head at a perpendicular angle. Right? So that makes sense, that it's orthogonal. So if you're going in direction of max rate of change, you're headed orthogonal to the contour lines. And what about the direction of greatest negative rate of change? So max negative rate of change. So what would the direction of that be? This just falls right out. So tell me where to stop. Where's max negative rate of change? There, right? You're going to go down as fast as you can. So you're going to get to the next contour line as fast as you can. That's orthogonal. So it's exactly in the opposite direction. So the vector is, max rate of change, direction as a vector is 2, 1. And the rate of change will be? It'll be exactly the same as negative root 5, right? So the max rate of change is the magnitude of the gradient. The max negative rate of change is the opposite of the magnitude of the gradient, and you go in the exact opposite direction. Okay, what about direction rate of change equal to 0? Quick. Be tangent to both of those, right? If you want to go in the direction rate of change of 0, there's two ways. You're going to walk along the contour line because that's where z stays constant. So there's two ways to do that. I can go this way or exactly opposite that way. That's when alpha equals pi over 2, 3 pi over 2. Max negative rate of change is when alpha equals pi. The opposite direction of pi equals, or alpha equals 0. Pi is the exact opposite direction as the direction of the gradient. And then two directions orthogonal to those give direction of rate of change of 0 means you're walking along contour lines, or you're walking around the mountain without going up or down. There's two ways to do it.